All right, so I want to keep going with doing solutions to a few of these assigned daily problems. So these are the going back to the Rankine power cycle problems. And let's start with number 5. So this one says the working fluid is water. We have superheated vapor this time entering the turbine. And that superheated vapor has a pressure of 10 megapascals and a temperature of 480 degrees Celsius. The condenser pressure, remember that's constant pressure, so it's the same at the inlet and the exit, is 6 kilopascals, so very low. 6% of regular atmospheric pressure. And this is an isentropic efficiency problem. So we can write this as the turbine has an isentropic efficiency of 0.8, 80%. And the pump has an isentropic efficiency of 70%, 0.7. And we want to figure out a few things. So we want to figure out the rate of, well, I'll just write it as Q dot for the boiler over the mass flow rate. I have it as sub B because that's what I've always called it, but this is a superheated vapor going into the turbine, so that's actually a steam generator. And then the thermal efficiency. And then Q dot over M dot for the condenser. So those are the three things. And as always, we can get all those three things just by calculating the enthalpies at all the different states. One thing about these isentropic efficiencies is, so at the turbine, well, first let me say, so this turbine isentropic efficiency and the pump isentropic efficiency are always less than, well, I guess they wouldn't be equal to 1 or you would just ignore it, but they're always less than 1. And so, and they relate to, you can think of it as Q dot over M dot true compared to Q dot over M dot isentropic. Okay, so if you think of it this way, you can always remember the way these ratios work. So for the isentropic case, we would calculate these states as like state 2s and state 4s. Yeah. And so notice that for the turbine, Q dot over M dot has to be smaller than, say this is the true one, has to be smaller than Q dot over M dot isentropic. It just makes sense if you think about the way adding inefficiency works. For the pump, it's opposite. Damn it. These are not Q's, these are W's. So all those turbine and pump Q's that I wrote should be W dots. I mean, that's just what the turbine and the pump do. And so that tells you that what you need in this case is, so since this isentropic efficiency is less than 1, you can rewrite this as WT dot over M dot isentropic. Well, let's write it like this. True is equal to the isentropic efficiency for the turbine times WT dot over M dot in the isentropic case. And so you can rewrite that as, so this is for the, okay, I have to correct one more thing that went along with writing those heats. So for the, no, those are still the right states. Okay, so you can rewrite this because we have an expression in terms of enthalpies for the turbine work rate over the mass flow rate. So H2 minus H1 is equal to the isentropic efficiency times H2S minus H1. And let me make sure I have those signs right. These should be reversed. So H1 minus H2 is equal to eta times the quantity H1 minus H2S. Okay, so that wasn't the smoothest description, but it's sort of the way that you can think your way through this to remind yourself what the relationships need to be with these isentropic efficiencies and the sort of ideal enthalpies compared to the true enthalpies. You can do the same thing for the pump. For the pump, since you're adding that work at the pump, inefficiency increases the work that needs to be done by the pump. So in this case, we have a switched relationship. This time, the work done in the ideal case is going to be less than the work for the true case. So W dot for the pump isentropic over m dot is going to be less than W dot for the pump for the Q case. And so that means that eta for the pump is equal to W for the pump over m dot in the isentropic case. That's equal to W sub P dot over m dot for the true case. So that's where you come up with this, the fact that you're multiplying eta by the ideal values for the pump, and you're multiplying it to the true values for the turbine. Okay, if you think about it that way, it makes sense. And then we can write that in terms of enthalpies as eta pump. We have the isentropic case for the pump. It's going from state 3 to 4, and this would be, so this is H4 minus H4S minus H3, and that's equal to H4 minus H3. So if you want to think that stuff through, you don't want to keep going back to the equations. That's how it makes sense. All right, so let's draw the
efficiency times equal to the isentropic.
The efficiency, did I do that backwards? Yes, did I? Yes, I did. Right, you're exactly right. Yeah. So this should be true. This should be isentropic. You can think it through that way. I just did not do it successfully. So this should be true. And that means that this should be 4 and this one should be 4s. Okay, well, let's draw what's going on in this temperature entropy diagram. We have a superheated vapor going into the turbine in this case, so our state 1 is out here. Our state 2s is there. State 3. (4s). And now in these two isentropic states, those are the two with the vertical paths, we're going to be introducing entropy. And so the true state 2 is there. And the true state 4 is here. You can see that the entropy is higher at the true state in each of these cases than at the ideal state. This should be, say, 2. And this should say 4. All right, well, let's write out these states and figure out what we know at each of these. So Here's state 1, state 2, 3, 4. We can see that state 1 is a superheated vapor. And going from state 1 to state 2, we have, and actually, let me write, so for these things that we're going to calculate, let's do the calculations in the isentropic cases. So this is an isentropic turbine. Then from 2s to 3, we have an isobaric condenser. Then from 3 to 4s, we have an isentropic pump. And so we're going to do this problem to start with as if we're just going to come up with all the enthalpies as if it was just the black path, and then we'll use the isentropic efficiencies to make the adjustments. Okay, so state 2s, that is a saturated mix. State 3 is a saturated liquid. And state 4 is a compressed liquid. So for states 1 and 4, we need to have 2 properties to find states in tables or whatever. For states 2s and 3, we can calculate those with 1 property. With 2s, we also need to know a quality of that mixture. State 1, we are given the pressure, so P1 is 10 times 10 to the 6 pascals. And we're given the temperature, 480 degrees Celsius. And so that's a superheated vapor, but we have 2 properties, so we can look everything up there. So let's right away look up the enthalpy at that state, and you get 3321.4 times 10 to the 3rd. And let's also look up the entropy at that state, and that is 6.5282 times 10 to the 3rd. Why would we look up the entropy at that state? It's pretty much always the same reason when we do it. The sort of flow of this problem is, this is an isentropic process. So if we can find the entropy here, then we know the entropy here, and then we can use that to find the quality. State 2 is also 6.5282 times 10 to the 3rd. The pressure for the condenser, so that's here. Is 6 kilopascals, so 6 times 10 to the 3rd, and that's also the pressure at 3. Really, we should probably write 2s here for the entropy, because that's not the entropy of the actual state. That's the entropy if we're assuming, hey, that's the entropy if we're assuming that this is an isentropic process, which it isn't. Okay, what else do we know? Well, I didn't write this, but it's a, this process from 4s back to 1 is an isobaric boiler. And so that means that the pressure at 4s is 10 times 10 to the 6th pascals. And, okay, well, that is going to be enough for us to use the incompressible assumption to calculate the enthalpy at that state 4. Okay, a saturated liquid. So going to state 3, a saturated liquid at a pressure of 6 times 10 to the 3rd. We can just look up H3 is 151.53 times 10 to the 3rd. And we can also look up S3, which is 0.5210 times 10 to the 3rd. Since this pump is isentropic, that's also S4, although I'm going to go a different way, but you could do sort of a reverse lookup now for this compressed liquid because we have two properties if you wanted to do it out of the table. All right, so that's everything that we know before we start doing calculations with these values. So I'm going to start with the state 2s. So there's stuff we can figure out from the state 2s. And that is since, so this is a saturated mix. We know the pressure. We just don't know what the quality is, but we can get the quality from the entropy. So 6.5282 times 10 to the 3rd is equal to the quality times the entropy for the saturated vapor. And if you look that up at this pressure, it's 8.3304 times 10 to the 3rd. And then plus 1 minus the quality times the entropy of the saturated liquid at that pressure. Look that up and it's 0.5210 times 10 to the 3rd. And solve for the quality and you get 0.769. And now that we have that quality, we can calculate the enthalpy, which is really all we want for these is to get the enthalpies. So H2S is 0.769 times the enthalpy of the saturated vapor at that pressure, which is 2567.4 times 10 to the 3rd, plus 0.231 times the enthalpy for the saturated liquid at that pressure, which is 151.53 times 10 to the 3rd. And you get an enthalpy value of H2S of 2009.33 times 10 to the 3rd. So there it is. Now we have this enthalpy value that goes there. And now we have enthalpies at states 1, 2s, and 3. We just need to get it at state 4. So now let's see what we know at state 4. Well, for the pump, we know we have that alternate form of assuming an incompressible material that says W dot over M dot, which is equal to H4 minus H3. And in our case, this would be 4S. We can also calculate this as, since we can assume that it's incompressible, this is equal to the specific volume at either one of these states, but I'll take 3, times the change in pressure. So P4 minus P3. So H4S, if I rearrange this, is equal to H3 plus the specific volume of water times the pressure at state 4, which is 10 times 10 to the 6, minus the pressure at state 3, which is 6 times 10 to the 3rd. Plug all the values in, and you get 161.5 times 10 to the 3rd. And so now we have our H4S. And now we have all 4 of those enthalpy values. We can calculate pretty much anything we want with what we have. These are the values assuming isentropic. So now we have to use those. We have to use those isentropic efficiencies to calculate the true values. So let's first do the. Now we're going to use the isentropic efficiencies. I'll do the turbine first. So we figured out that for the turbine, we're going to get the true enthalpies, we're going to multiply the isentropic efficiency to the ideal enthalpies differences. So H1 minus H2 is equal to 0.8 times H1 minus H2S. The only one we're looking for is H2, so we can rewrite this as H1 minus 0.8 times this difference. Plug the values in, and let's see. So H2 is equal to 3321.4 times 10 to the third minus 0.8 times the quantity 3321.4 times 10 to the third minus 2009.33 times 10 to the third. And you get that true enthalpy at state 2 is equal to 22 71.7 times 10 to the third. Okay, now we'll do it for the pump. So this time, like I tried to stress before we kind of started this problem, we have the isentropic efficiency multiplied by the true values instead of the ideal values. So we have 0.7 times the quantity H4 minus H3 is equal to H4S minus H3. So H4 minus H3 is equal to 1 over 0.7 times the quantity H4S minus H3. So H4 is equal to H3 plus 1 over 0.7 times the quantity H4S minus H3. So that's 151.53 times 10 to the third plus 1 over 0.7 times the quantity 161.5 times 10 to the third minus 151.53 times 10 to the third. And you get H4 is equal to 165.8 times 10 to the third. And now we can just plug in whatever enthalpies we need for the different calculations. So the first thing we're trying to calculate is Q dot for the boiler over M dot. That's just equal to H1 minus H4. That's 3321.4 times 10 to the third minus 161.5 times 10 to the third. And so you get a value of 3359.9 times 10 to the third joules per kilogram. Second, we want to calculate the thermal efficiency. That's equal to 1 minus the quantity H2 minus H3 divided by the quantity H1 minus H4 again, just plug those values in and you get 0.328. And then C, we want to calculate Q dot at the condenser divided by M dot. That's H2 minus H3. Plug those in and you get 2120.2 times 10 to the third joules per kilogram. If we hadn't been given those isentropic efficiency values, and we just assumed it was this ideal case, how would these change? So first, the rate of heat flow at the boiler, would that be bigger or smaller?
Well, you need less heat.
You would need less heat. You would need less heat. Right, right. And the thermal efficiency, would that be lower or higher?
Higher.
That would be higher. You have a more efficient thing. And then the rate of heat flow at the condenser?
Lower.
That would be higher, wouldn't it? H2S compared to H2. So H2S is, the ideal state would be smaller. So QC ideal would be less. Yeah, you're right. Any questions about that one? Okay, so that was a problem. I think there's two problems on that assignment that have isentropic efficiencies. And then at the end, there are two problems that have reheat. So I'm going to do an example that has reheat. This working fluid, again, is water. And it says steam, so this is superheated vapor at 10 megapascals and 600 degrees Celsius enters the first stage turbine. The steam, again, this is superheated in this case, leaving the reheat section has a temperature of 500 degrees Celsius. The condenser pressure is 6 kilopascals. The quality at the exit of the second stage turbine is 0.9. And we just want to calculate the thermal efficiency. Okay, so we have a lot of different states here. Let's draw what's going on first. Coming out of the steam generator, we are going to a superheated state. So I'm going to call this 1A. It goes through that first stage turbine to the state, I'm going to call that 2A. Then it goes back to the steam generator to the state 1B. And now it returns to the way we're used to thinking of the behavior through the turbine to this point 2B. Then it goes through the condenser to the state 3, the pump to the state 4, and back to the start. So let's write out these states. So there's state 1A, 1B, 1A to 2A, to 1B, to 2B, to 3, to 4. From 1A to 2A, that's an isentropic turbine. From 2A to 1B, that's an isobaric boiler. It's really a steam generator. From 1B to 2B, that's another isentropic turbine. From 2B to 3A, that is an isobaric condenser. And then from 3 to 4 is an isentropic pump. And then from 4 back to 1A, that is an isobaric boiler. Again, that's a steam generator, actually, because we're going to these superheated states. And what are the phases at these different places? At 1A, that's superheated vapor. We are given that the temperature there is, well, that the pressure is 10 times 10 to the 6, and the temperature is 600 degrees Celsius. So we can look up anything we need there. So H1A, we'll just look that up, and that is 3625.3 times 10 to the third. And we'll look up the entropy. That's 6.9029 times 10 to the third. Why do we look up the entropy there? Same reason as always. It's because since this is an isentropic turbine, this first stage turbine, we can use that as one of the properties that we need, whether it's a mixed phase at saturation here, or whether it's still a superheated vapor. In this case, it's a superheated vapor. At 1B, so after it's gone through that steam generator again, we have a superheated vapor. And we are told that the temperature there is 500 degrees Celsius. At 2B, this is a mixture with a quality of 0.9. And a pressure of 6 times 10 to the third pascals. And so since we have the quality already, we know that it's at saturation, we have the pressure, we can just calculate right away these values. I'll do that in a second, but we already know that that information is available to us. Then at state 3, that's a saturated liquid. We know that the pressure is 6 times 10 to the third because that condenser is isobaric. And so a saturated liquid with a known pressure, we can look up anything we want. So our H3, we'll just look that up in the table right now, is 151.53 times 10 to the third. And we'll look up the entropy. That is 0.5210 times 10 to the third. And we'll look that up because the next process is isentropic. And so we also know that that is the entropy for state 4. State 4 is a compressed liquid. We know that the pressure is the same at state 1A because that's an isobaric boiler. And so the pressure is 10 megapascals, 10 times 10 to the 6. And the entropy is the same as it was at state 3, so S4 is equal to 0.5210 times 10 to the third. So now, like in a problem like this, I think really once you have all your information laid out, you just have to figure out the direction that you're going to proceed. I think the way to go is just calculate the stuff that you know you can calculate. So let's go straight to 2B, use that quality and come up with the enthalpy there. And we can come up with the entropy there too. So at the state 2B, H2B is equal to the quality times the enthalpy at the saturated vapor state from the table. So that's 2567.4 times 10 to the third plus 0.1 times 151.53 times 10 to the third. And you get an enthalpy of 2325.81 times 10 to the third. And you can do the same thing with entropy. So S2B is 0.9 times the entropy for the saturated vapor, which is 8.3304 times 10 to the third. plus 0.1 times 0.5210 times 10 to the third, and you get 7.5495 times 10 to the third. All right, well, these now are values at this state 2b. We can make the incompressible assumption to calculate the enthalpy at state 4. We almost always do that. You also could use those two properties to do a reverse lookup, but I'm just going to use that H4 is equal to H3 plus specific volume times the quantity pressure at state 4 minus pressure at state 3. We have all those values, and if you plug them in, you get that H4 is equal to 161.5 times 10 to the third. Okay, what do we still need? We have enthalpies everywhere now except the states 2A after that first stage turbine and 1B after it returns to the steam generator. So next, let's go to the state 1B. So notice that we calculated the entropy at 2B, and because that turbine is isentropic, we also know the entropy at state 1B. So 1B, we know that the 1B entropy is 7.5495 times 10 to the third. And we know that the temperature is 500 degrees Celsius. That's two properties, so we can do a reverse lookup on that. And what you see in this case is that the pressure has to be 1.5 times 10 to the 6 pascals. And so now you can look up the enthalpy there. So H1B is equal to, does anyone have a table with them? You guys? Okay. 1.5 megapascals. Okay, so we want superheated vapor, water. So at 1.5 megapascals, the enthalpy at 500 degrees Celsius is 3473.1. Times 10 to the third. And that pressure at 1B also has to be the pressure at 2A. So the pressure at 2A also has to be 1.5 times 10 to the 6. And the entropy has to be 6.9 times 10 to the third. So we're looking for a place where we have a pressure of 1.5 megapascals and an entropy of 6.9. So that is, let's call it this one, 6.84. So look up the enthalpy there, and the enthalpy is 2992.7. Times 10 to the third. And now we have the enthalpies at all those states. Okay, so that was, I mean, that's just always tedious. Just thinking your way around, like you have, this has to be this, like, but okay, so now we're going back to more of the sort of conceptual stuff. All right, so we want to calculate the thermal efficiency of this now that we have all those enthalpies. So the thermal efficiency, we have not done that for a reheat in an example problem yet. So how do you do that? Well, the definition of this thermal efficiency is the total rate of work and you can think of that as divided by m dot if you want, divided by the total rate of heat input. At the boiler. I'll call that net, and I'll divide that by m dot 2. So this is the work dot for turbine 1 divided by m dot plus W dot for turbine 2 divided by m dot minus the work put into the pump divided by m dot, all divided by the heats at those two steam generators. So Q dot for boiler 1 divided by m dot plus Q dot for boiler 2 divided by m dot. So we just have to come up with enthalpy expressions for all of these things. So turbine 1. This W dot over M dot is, so that is the process from 1A to 2A. So this is just going to be H1A minus H2A. This ratio for turbine 2, so this is the one that goes from 1B to 2B. So this is just going to be H1B minus H2B. The work for the pump, this ratio, because you have work coming in instead of going out, there's the sign switch. This is between states 3 and 4. And so this is going to be H4 minus H3. And now we have the 2 times through the steam generator, so that the ratio for boiler 1 that is from 4 to 1A. And so that is going to be H1A minus H4. Yeah. And then boiler 2, that ratio. So boiler 2 is going from state 2A to 1B. So that's going to be 1B minus 2A. And now we can put this all together. Eta is equal to H1A minus H2A plus H1B minus H2B minus H4 minus H3, minus the quantity H4 minus H3. All divided by H1A minus H4 plus H1B minus H2A. Can you guys take a second and plug those into your calculators for me? I'll let the right answer. Ooh, that's terrible. 0.144. Feels low, but I don't have anything better, so we'll go with that for now. Anybody have any questions about the flow of the problem anyways? Okay, well, let's call it a day. So next time, I think what I'm planning to do on Thursday is just talk a little bit about refrigeration cycles, but not a lot. I haven't decided yet if I'm going to give you problems on that, and then we'll do just sort of wrap up and stuff next week before we have a third exam coming up. I didn't. Let me look at when that is. Okay, so we have exam 3. Oh, this is the one. Oh, this is the class where, so that is not the exam 3. So we're going to have exam 3 next week. I guess let's just do it on Thursday. And so a week from Thursday, we'll have exam 3, and then we'll have the final a week later. I'll figure out what topics are going to be on exam 3, and I'll tell you all this Thursday. So you have a week to get ready. But I think probably like there'll be some stuff from the end that I'll save until the final. But anyways, I'll tell you exactly what's going to be on exam 3 on Thursday of this week. Okay, that's all I got.